Throughout human history, bridges have been milestones of progress, measurements of man's increasing ability to overcome the obstacles that once restricted his development. Today, a nation's progress depends to a large extent on an efficient and effective transportation network linked together by bridges designed to span every type of natural barrier. Modern wheels, born to serve in a great transportation system, race over the once impassable barriers and speed on to the next triumph of the bridge builder's art. The development of our country owes much to the advance in the science of bridge building, which hastened the growth of our cities and of large sections of the country. Linking the country are tens of thousands of railroad bridges and hundreds of thousands of highway bridges, the world's finest transportation system, spanning gullies, ravines, and valleys, streams, rivers, and harbors, tying each solid land area to its neighbor, literally weaving America into a closely knit fabric with tough strands of steel. Here, where the Monongahela and Allegheny rivers meet to flow westward as the Ohio, was the Pittsburgh of the future, the city which George Washington considered the gateway to the West. Pittsburgh is today the city of bridges and the home of the largest and best-known builders of bridges, the American Bridge Division of United States Steel. In the shadow of the home of these bridge builders are many examples of their engineering skills. A showroom of bridges. All are vital links in Pittsburgh's transportation system and the country's transportation system. Structures based on a mastery of mathematics and physics and chemistry and geology and aerodynamics and other exact sciences. The suspension bridge has been called the bridge of the future, since it is capable of meeting the demands for spanning greater and greater distances. Suspension bridges have personalities of their own, even though they may look alike to the casual observer. For example, these two bridges appear to be of the same construction. A closer look, however, shows that one is the conventional type with two tower piers and two anchorages, while the other is the self-anchored type with two tower piers, but with the roadway itself serving as the anchorage. Crossing the Monongahela River is a good example of the typical suspension bridge with its anchorage foundations and the foundations supporting the towers. The main cables, built up of thousands of parallel wires, run from anchorage to anchorage and are draped over the towers for support. And from cable bands, spaced at regular intervals, wire rope suspenders hold up the bridge below, hence the name suspension bridge. Spanning the Allegheny River are three examples of the self-anchored type suspension bridge with two tower piers and no anchorage foundations. Their main supports are links of forged steel eye-bars, much like giant bicycle chains. The suspenders, too, are made up of eye-bars. As though lifting itself by the bootstraps, the main supporting chains are fastened directly to the longitudinal girders which carry the roadway. The construction of a suspension bridge is exciting and dramatic, a challenge to bridge designers, to the fabricators of the integral parts, to the steel workers who convert lines from a blueprint into lasting monuments of steel. Methods of construction often vary because each bridge must be individually designed to meet existing conditions. Not only are there entirely different types of suspension bridges, but the methods of construction differ also. For instance, cables are generally built up of thousands of single parallel wires banded together to form the main supporting cables. But in the case of the Paseo Bridge over the Missouri River at Kansas City, instead of building cables of single wires laid side by side, they are constructed of 37 pre-formed bridge strands. The strands have been pre-stressed and cut to exact length, with the ends permanently set into sockets, designed to fit perfectly into their anchorage seats. Before the main cables were installed, the roadway itself was supported by temporary falsework. This gave the bridgeman a working surface for the construction of the cables. Rollers down the center of the bridge not only protect the galvanized strands, they also ease the work of pulling the husky steel strands from their reels located beneath the structure. Each of these reels holds a single strand with sockets attached at both ends. Each cable strand must be hoisted to final position across the saddles on top of the towers. The sockets at the end of the strands are permanently seated in their anchorages. The pre-calculated length of each strand must be maintained if it is to exactly fit its anchorage. To keep any strands from twisting, which would lengthen or shorten them, the red lines must be kept parallel. Aluminum filler strips fill the crevices between the strands in the cable. This makes for a smooth, rounded out surface so that the saddle will fit snugly around the cable. After sockets are locked in place, final adjustments are made to bring the strands to an exact predetermined tension. This is done at night when all the wires are at a more nearly uniform temperature. Information is telephoned from the center of the span to the crews at the anchorages. The precision and care of bridge construction is well demonstrated by the accuracy with which the cable strands pass over the saddle. A simple hydraulic compacting device squeezes the cable into its final size and shape, and the cable is temporarily banded. Engineers locate the exact positions where the cable bands are to be attached. Safety lines are a necessary precaution. After all, bridgemen aren't birds. Special aluminum castings give a smooth, firm base for the cable bands. A large moving scaffold hung from wooden rollers serves as a working platform. The wooden rollers protect the galvanized wires of the cable from damage. With the band secure, suspenders are hung into position along the cable's entire length. Bridge suspender ropes, like the cable strands, were accurately pre-stressed, cut and fitted with sockets at the factory. As cable bands and suspenders are attached, the sockets on the ends of the suspenders are fitted neatly into their seats on the girders beneath the roadway and are secured by bolts through the stiffener angles. Long filler strips round out the cable for the wire wrapping operation. A wrapping machine spins 3 wires simultaneously, covering the cable throughout its entire length, except for the areas next to the cable bands. These areas are hand wrapped. A heavy application of red lead paste provides an excellent protective coating for the cable. The beginning of one spool of wrapping wire is neatly butt welded to the end of the previous spool. The splice is then heated and regalvanized for permanent protection. And the wrapping continues. After the last suspender socket is fastened to its seat on the girders, the temporary falsework supporting the roadway is removed. And there you are. A true suspension bridge with the road hung from above. A road suspended by steel wires and man's ingenuity. There was an even greater challenge in erecting the Delaware Memorial Bridge, spanning the Delaware at Wilmington, linking the states of Delaware and New Jersey. To span this river, the engineers designed the conventional suspension bridge with 2 anchorages and 2 tower piers. Conventional? Yes, but unusual in many details. The construction of the tower piers and anchorage foundations was a king-size engineering feat. For instance, the west anchorage, built by the open dredge caisson method, was the largest caisson in cross-section ever built and contained 60 dredge wells, each 15 feet in diameter. A cofferdam was used in the construction of the east anchorage. The massive piers, built of many tons of steel and concrete, make a solid base for these eye-bars to which the main cable strands will be anchored. They look like clusters of giant needles awaiting their threads of steel. As soon as the tower piers were completed, the steel tower construction was started. Floating derricks erected the lower sections and the vertical traveler. As the work progressed, the vertical traveler moved upward to set the heavy tower sections. These are the main vertical supports for the span. The towers rise to the height of a 45-story building above the bottom of the piers. That's about as high as the home office of American Bridge. Naturally, before beginning to build up the cables, there must be a safe footing for the workmen. To provide this safe footing, 2 catwalks supported by 8 prefabricated wire bridge ropes, 2 inches in diameter, are strung over the 2 towers linking the anchorages. This was the only operation during the erection of the bridge which temporarily held up river traffic. During the rest of construction, ships went up and down the river as usual. The Delaware is a busy river. These catwalks, invented by American bridge engineers, are made of cyclone chain link fencing, supported by wooden cleats attached to the catwalk cables. This type catwalk has been used on many major suspension bridges in this country. It unfolds readily, like accordion pleating, and actually becomes a temporary suspension bridge, a sort of harbinger of the real thing to follow. The cables holding up the catwalks serve another purpose. Eventually, they go back to the factory, are cut to length and socketed to form the suspenders for the main bridge. Cable hand railings stretched along wooden posts on both sides of the catwalks give the men additional protection. These men are constantly working in the shadow of the slogan, "Safety First," coined many years ago by United States Steel. On a job like this, you have to reckon with wind. So a web of temporary cables is put up to resist the movement of the catwalks. Then, to steady them further, temporary struts tie the 2 catwalks together. The struts, placed at the center and quarter points, make them more rigid. The workmen erect the tramway supports for the installation of the endless hauling ropes, to which the spinning wheels will be mounted, for the purpose of pulling loops of wire from large supply reels back and forth to form the cables. To speed up cable spinning, double-grooved wheels are pulled across the river by the endless cables of the tramway system. Each wheel lays 4 wires on every trip. Since there is another wheel coming from the other anchorage at the same time, 8 wires are laid each time the spinning wheels cross the river, the wheels passing each other in the exact center of the bridge on each crossing. The spinning wheels dip sharply over the cable bent and go down to the anchorage. Here, the wires are looped over the fittings attached to the eye-bars. Then the wheel is reloaded with 2 new loops from the large wire reels and is made ready for the return trip across the river. And of course, the same transfer is made at the anchorage on the other side of the Delaware at the same time. The workmen receive the two lower wires of the loop, called dead wires, from the spinning wheel and place them into the strand. As each strand is completed, temporary bands hold the wires in place. The spinning wheels travel at a pretty good clip. To warn the busy men on the catwalks of their approach, a cowbell attached to the wheel rings a constant alarm. Uniform tension is maintained during the spinning operation by a series of counterweights and sheaves housed in the spinning tower. There is not much time lost between reels. Another is always waiting to be rolled into position. The ends of the wires spliced together and the spinning continued. In splicing the wires, an ingenious device is used. A steel sleeve with right and left hand threads draws the threaded ends together. As the ends are beveled, they will interlock and thus prevent accidental unscrewing. According to the prearranged schedule, the 16-ton reels are trucked from the wire plant, loaded onto barges by locomotive crane, then towed to the bridge anchorage, assuring a constant supply of wire throughout the spinning operations. The cable reels are hoisted to a working platform on top of the anchorage. Work continues even during the cold winter months. The spinning doesn't stop, even for darkness. The day crew leaves, another picks up the work under the floodlights. Spinning, constantly spinning, night and day, around the clock. While struts and temporary cables help steady the catwalks, sometimes the main cables have to tussle with the bridge builder's greatest annoyance, the wind. Just as important as logistics in wartime is the storing and delivering of materials for bridge construction. The municipal dock at Wilmington, with its many acres of storage area, served as the depot for the receipt and transfer of the many tons of material needed for this bridge. And loaded with this material is the inevitable barge, always waiting down below, with just what is needed above. This is not exactly what we'd call an architectural gem, but this snug shell protects the hoisting engineer from the icy blasts while he keeps the reels of wire moving so that the spinning can go right on, night and day, up from the anchorage, over the cable bend, and off across the Delaware. The wheels shuttling back and forth, laying down wires. 436 of them building up into a single strand. 19 strands paired off with 19 eye-bars, and the 19 strands converging into a single giant cable of 8,284 wires, waiting to be banded together permanently. Before banding, the main cables must be compacted to their final size. During this process, the catwalks were hung from the main cables, while the 2-inch wire ropes which had previously supported the catwalks were returned to the wire plant for conversion into suspender ropes. The cables are now ready to receive their cable bands. Workmen using chain hoists lift the bands to trolleys which roll them to their positions. Each cable band from which suspenders are to be hung was designed for its particular location on the main cable. The cable bands are securely attached over a coating of red lead paste and then tightened with sturdy bolts. The 2-inch suspenders, which were cut from the original catwalk cable, are attached to the cable bands, the ends left dangling until their trusses are ready down below. The suspenders do not have long to wait. While they were being installed, steel cords, diagonals, and verticals were assembled at the depot and riveted into large truss sections 20 feet deep, loaded aboard barges, and floated to the bridge site. The erection of the roadway trusses starts at the towers and works outward in both directions at the same time. traveler derricks hoist the truss sections into positions. The longitudinal roadway trusses are tied together with heavy transverse trusses known as floor beams. These floor beams, together with the lateral bracing system, add stiffness to the entire structure. The traveler derricks work their way to the center and are ready to close a span of 2,150 feet with the last truss sections. And the suspenders hanging from the cable bands on the main cables are ready for the last trusses. And here is one of the last cord sections decorated with briskly flying stars and stripes, the bridgeman's symbol for closing the span. The men know that it will fit because every steel member has been made exactly to the engineer's blueprints. On bridge work, all members are temporarily connected with drift pins and bolts, which are later replaced with rivets. The two traveler derricks have finally worked their way face to face. They seem to be bowing ceremoniously as though congratulating each other on a job well done. White-hot rivets permanently connect the sections as drift pins and bolts are removed. One of the last cord sections slides into place. The slings are removed. This is hardly the place for anyone who is jittery. It takes courage plus to be a bridgeman, but these fellows are no more concerned about their perch high up over the cold Delaware below than if they were playing a game of gin rummy in the tool shanty. It's their job. One of the last verticals is set into position, and at the upper end, the suspender is seated. Another vertical going into position. All in a day's work, a bridgeman's work, that is. Straight up so that he can place the suspender in its seat. Just a single bolt through the stiffener is all that's necessary to hold the suspender in place permanently. These men are too busy to gaze at the ships below. Besides, there's always another one on the way. After the verticals are in place, the diagonals are set. A little fancy footwork helps, and the spud wrench finds the matching hole. Here's an easy way down. Fun, isn't it? Well, anyway, he's at home up here. Double wire rope slings not only provide additional safety, but also the member is in the exact position desired by the workman above. With the verticals and diagonals all set, the structure is ready to receive the top cords. The gusset plates receive the ends of the diagonals and verticals, then the last section is set into place. Another straight up climb, and the vertical is connected to the top cord. Finally, the splice plates, already temporarily bolted to the member, are placed. Not a finished bridge yet, but it's easy for a bridgeman to picture the heavy traffic which will soon be speeding across the structure. After the roadway system has been filled in at the center of the span, the unfinished sections between the anchorages and the ends of the roadway trusses are completed. A wrapping machine, similar to the one used on the Paseo Bridge, covers the main cable with a tight-fitting steel wire overcoat. Permanent protection against the weather is provided by the heavy red lead paste which coats the entire cable. From the amount of red lead on the workmen's clothes, they would seem to be preparing for a rough winter. From a distance, it's difficult to judge the massive sizes of the individual members of a suspension bridge. Add to the main suspension bridge the deck girders, the deck truss approaches and overpasses at its terminals, and you get a good idea of the teamwork among all the men and the many firms, large and small, who played a part in making the bridge a reality. What a job. There were over 175 subcontractors, each tops in his particular field, and all working from the same master set of blueprints and specifications. They so dovetailed and synchronized their individual chores that a 3,650-foot suspension bridge from anchorage to anchorage and almost another 7,000 feet of approaches was ready for public use within 18 months after the first steelwork for the superstructure was started. Today, spanning the often turbulent waters of the mighty Delaware, with ships from every port flying back and forth in endless procession, this beautiful bridge is truly a fitting memorial to the World War II heroic dead of Delaware and New Jersey. And another suspension bridge closes a gap in America's great transportation system.